Welcome to Lecture 4 on the new astronomy and cosmology. As I said in the lecture on Aristotelian scholasticism, because in the Aristotelian system there is a fundamental division between an imperfect and mutable sublunar world and an unchanging and immutable celestial world, astronomy always had been deemed a science worthy of fine and reverent minds, and any changes in thinking about astronomy always threatened to pose the most fundamental challenges to the entire Aristotelian scholastic system. So to talk about the new astronomy is not merely to talk about, from a 20th century perspective, human science and discovery, but to talk at some of the deepest philosophical levels about the challenge to the dominance of Aristotelian scholasticism. The astronomy that the Aristotelians and scholastics had adopted was that of Claudius Ptolemy, a Greek astronomer of the 2nd century AD. It was wonderfully consistent with the scholastic worldview. It held that the Earth was at the center of the universe, which, far from being a place of importance, meant that it was at furthest remove from God. That is the drama of the Earth being at the center of the universe. And it held that the moon, the planets, the sun, and an orb of fixed stars revolved around the Earth in perfect circular motion. We said in discussing the Disputatio that one of the roles of experience was that a theory must account for the phenomena. And the Ptolemaic notion of perfect circular motion of all heavenly bodies around the Earth had produced almost from the start certain anomalies in terms of accounting for phenomena. Anomalies that we now understand, both by placing the sun at the center of the solar system and by our understanding of the planetary orbits as elliptical and not circular. To account for the phenomena that posed problems to the Ptolemaic astronomy, astronomers added more and more of two things in particular. First, what they called eccentric orbits, orbits that were perfectly circular, but the Earth was not directly at their center, and what were called epicycles, in which the orbit that was perfectly circular around the Earth of a planet was seen as the center of an orbit, such that one would have the center of the orbit of Mars here, the planet moving around it, and that would account for retrograde motion that we now would explain by other means. And the Ptolemaic system became burdened by more and more eccentric orbits and epicycles to account for the data of astronomy. Among the intellectual movements that arose to challenge Aristotelian scholasticism was a revival of a line of thought that traced its lineage back to the mystical ancient Greek mathematician Pythagoras. We call this, in the early modern world, Neo-Pythagorean thought, where the scholastics viewed God's creation in terms of perfections and purposes. The Neo-Pythagoreans viewed the creation in terms of mathematics and geometry. Now, I don't want to overstate this. Well, in fact, I would love to overstate this, but honesty compels me not to. In the last generation of scholarship, we have learned a great deal about major developments in mathematics and the application of mathematics to motion that preceded the 17th century and preceded what I am terming Neo-Pythagorean thought. Nonetheless, the worldview of Aristotelian scholasticism is above all and quite dramatically qualitative, not quantitative in its conception of the universe. In what way does substance and form manifest what qualities of perfection in the creation? And the scholastic worldview is essentialistic and teleological in its view of motion. Let's explain. If you think back to the scholastic view of the nature of any being, it has a particular form, one form, that has been actualized from a set of the limited possibilities of any substance. That means it has an essence, something that makes it uniquely what it is, that distinguishes it categorically from all other things. Teleological recall means that it expresses a purpose, that it acts for an end, a goal. The motion in the scholastic system expresses the essence, the perfections, the qualities, and the purposes of something. So, for example, if we asked a scholastic about the behavior of certain things in physics, why does a rock fall? A rock falls because it is seeking its proper physical place in the ontological universe on the great chain of being. It is at furthest remove from God, a rock. It is all body, it has no soul, so a rock falls to secure its proper place in the universe. Fire rises because fire can purge body. It can purge flesh, and fire rises closer toward God. The motion of things express their peculiar, particular essence in the world. And motion expresses purpose. Rain falls in order that crops may grow. That is why rain falls. It is that fundamental view of reality and phenomena as qualitative and teleological that the Neo-Pythagoreans will challenge in terms of fundamental worldview. For the Neo-Pythagoreans, the divine mind, God, expressed itself in the order and harmonies and ratios of the creation. Reality, for a Neo-Pythagorean, emanating from the divinity itself, was numerical and geometrical. In addition, Pythagoreans saw the sun, luminous and perfectly circular, as a most special thing in the universe. The early Pythagoreans worshipped it. The later Neo-Pythagoreans saw it as a virtual emblem of the divinity, a stamp of God's likeness upon the creation, luminous and perfectly circular. When the astronomer Copernicus in the 16th century, and with very little initial influence, revised the Ptolemaic system to make it more circular and more harmonious. Otherwise, there was very little to choose between the systems. He placed the sun at the center of the universe, which allowed him to reduce, not eliminate, epicycles and eccentric orbits. And he termed that sun in his scientific work the lamp, the mind, the ruler of the universe, God visible. The most meticulous observer of the heavens in the early 17th century, the Danish astronomer Tycho Brahe, did not accept Copernicus's system. He did put the planets in orbit around the sun, but he put that sun and the orb of fixed stars in orbit around the Earth at the center. The inheritor of his data, however, was the extraordinary figure Johannes Kepler, Neo-Pythagorean, mystic, fortune teller, mathematician extraordinary, astrologer, and astronomer. The secret of Kepler's Herculean labor to fit Tycho's data to Copernicus's heliocentrism, the sun at the center of the system, was Kepler's deep faith long before any of his work allowed him to conclude it. Indeed, from the outset, that with the sun at the rightful center of the universe, the quantitative and geometrical harmonies and ratios of God's creation would be disclosed. Working on multivariables of time, distance, and motion, without either analytic geometry or the calculus, both of which would only be available later in the century, Kepler went through a mathematical ordeal of hard labor, only to fail and begin again, and through an inhuman combination of perseverance, chance, and his profound belief that the universe would reflect God's mathematical wisdom, God's mathematical order. He arrived in 1609 at his first two laws of planetary motion that brought order out of astronomy and Copernicus's system. The first law was a deep blow to Kepler, but the second depended on it and thus partly justified it. His first law was that the planets, including the Earth, described elliptic, not circular orbits around the sun. He wrote to a friend that the elliptical orbits were, quote, a cartful of dung, end quote. And I translate extremely politely here in case any of you are viewing or hearing this with your children. A cartful of shice, Kepler wrote. Posit the elliptic orbits, however, and his second law could be derived, that the line joining a planet to the sun, the radial vector, sweeps out equal areas in equal times. This geometrical order was exquisite for Kepler, but it was inadequate reward for abandoning the circular orbits, which almost all schools of philosophy, but in particular the Neo-Pythagoreans, saw as a perfect form. So for 10 more years, Kepler engaged in a computational struggle to find a harmony in this universe of ellipses. And in 1619, he found it. The square of the period of revolution of a planet is proportional to the cube of its average distance from the sun. Now the ellipses made sense. On the basis of them, God had manifested his wisdom in a magnificent correlation of the squares of the periods of revolution and the cubes of mean distances from the sun. The language of Neo-Pythagorean science is not the language of 20th century astronomy. In his great work, The Harmony of the World, Kepler introduced his third planetary law in the following language, quote, "I saw the dawn 18 months ago, the bright day 3 months ago, and several days ago, the brightest sun of a most wonderful vision. Now, nothing can restrain me. I let myself go in divine rage. I defy human beings with contempt in this. I have stolen the golden vessels of the Egyptians to create from them a sacred place for my God, far from the borders of Egypt. If you are angry with me, I shall bear it. The die is cast. I write for my contemporaries, or it does not matter, for the future. Perhaps my book will not have readers for 100 years, but God himself has waited 6,000 years for someone to gaze upon his creation with understanding." End quote. Kepler's correspondent and fellow mathematician and astronomer Galileo also believed passionately in Copernicus's system. But Galileo could not accept Kepler's laws. They seemed too speculative to him. And in fact, Kepler's laws of planetary motion did not receive confirmation in one sense until the work of Isaac Newton much later in the century, or in a different sense of confirmation until the space program. Galileo, however, did share Kepler's sense that nature was to be understood quantitatively and not in terms of perfections or purposes. Using the newly devised telescope, which he himself perfected, Galileo looked with fresh eyes, often at things which were not supposed to be there. For example, craters on what should have been a perfect spherical moon. He attempted to triangulate distances to demonstrate his points, and in the heavens and on earth, to mathematize our understanding of all motions. Debating with one opponent, an Aristotelian astronomer, Galileo wrote, "You don't know where to look. You look in the books of men, but the book of nature is where one must look." He also wrote, "And you have to know the language of the creation to understand that book. And the language of the book," Galileo wrote, "is number and geometrical form, without which one looks at nature in vain." Galileo's defense of the Copernican hypothesis certainly earned him great difficulties, but for many, the most dangerous aspect of his work and his most revolutionary assault upon Aristotelian scholasticism was his rejection of a physics and natural philosophy of perfections and purposes, and his substitution of a distinction between secondary and primary qualities. For Galileo, a whole set of our experiences of the world were what he termed secondary qualities. They were not what was out there, but how the human senses interacted with what was out there. The world was not yellow or red, sweet or bitter, beautiful or ugly. These were responses of the observer and the observer's sensory system to what was, in fact, out there. The primary qualities of nature, what remained in the object independently of human perception, what was real in God's natural creation, was quantity, dimension, shape, the measurable. All else was an effect of primary qualities upon our senses. What the scholastics called perfections for Galileo were human projections upon a natural world that was quantity in motion, to be understood in mathematical law. And Galileo's model of a law of falling bodies, true of all mass, independent of Aristotelian notions of perfections and of purposes, is the order for which he was striving. Where for the scholastics, bodies fell to reach their proper level in the chain of perfections, for Galileo, all matter could be explained in a terrestrial physics of uniform law. Hence, his law of falling bodies stated mathematically. Empirical observation, mathematical ordering, and, in theory at least, experimental test lead to laws of motion that are a true understanding of the reality that God created. Motion describes not the quality or purpose of something, but the relationship of bodies to time and to distance. He argued against Aristotle, and he argued against the notion of presumptive authority. But he threw Aristotle back at his critics, for Aristotle had observed the world. And it was Galileo who would write, quote, "If Aristotle were here today, he would agree with me." For Galileo, the great problem that his contemporaries could pose to him was the relationship of natural philosophy and theology. So, for example, convinced by his own inductive and mathematical reasoning of the truth of the Copernican hypothesis, he was aware that it was seemingly contradicted by Scripture, where, for example, in the book of Joshua, the sun is commanded to stand still so that the Israelites may win a victory. Defending himself, Galileo wrote a dramatic letter to the Grand Duchess Christina, in which he said, God is the author of two books, the book of Scripture and the book of nature. And he is a perfect author, and he does not contradict himself. What we observe and know to be true in nature cannot be false. And if Scripture seems to contradict what we know, the problem is not Scripture, but human interpretation of Scripture. Borrowing a phrase from a father of the church, Galileo said that Scripture is a book about how to go to heaven. It is not a book about how the heavens go. We all speak metaphorically of sunrise and sunset not because we are asserting a theory of astronomy, but because we are talking about ordinary human experience. Scripture speaks of the finger of God, the hand of God. Does that mean that one is an infidel if one does not ascribe body to the incorporeal deity? Scripture must be read in the light of human reason and human knowledge. The senses are from God, intellect is from God, reason and mathematics are from God. But in the universities it is taught that theology is the queen of the sciences and has preeminence. And Galileo says that is true in the sense of its subject matter, but not in the sense of its having eminent domain over other sciences. If you are ill, even though theology is the queen of the sciences, you go to a doctor of medicine, not a doctor of theology. If you need a contract drawn, even though theology is the queen of the sciences, you go to a doctor of law, not to a doctor of theology. And if you wish to know the natural system of physics and astronomy, you consult those who, through induction, mathematics, and experiment, know the natural order in which we find ourselves. When the Copernican hypothesis was forbidden to be taught, Galileo wrote that truth cannot be suppressed because you would have to force people not to look. You would have to force people to abandon what God had given them, experience and mathematical logic. God's creation, not this or that theologian's interpretation of Scripture, is the ultimate test. And quantity, not quality and purpose, is the stuff of reality. Galileo's works and Galileo's polemics were nothing less than an invitation to restructure our entire understanding of the world in which we found ourselves, to leave issues of perfection and purpose to theologians and to banish them from physics, from science, from what he would have termed natural philosophy. Invited by the Pope himself to write a book showing how problematic it was to choose between the Ptolemaic and the Copernican system. The conclusion the Pope urged upon him being that therefore in such difficult matters one must rely upon the authority of the Church. Galileo satisfied that demand in only the most nominal sense, but in terms of the substance of his dialogue concerning the two great world systems, the Copernican battered the Ptolemaic scholastic from intellectual pillar to intellectual post. And Galileo was tried for the crime of teaching as true the Copernican hypothesis. His enemies were also, we know, as deeply concerned that his primary and secondary qualities would make it impossible to explain the Eucharist, the transformation of the wine and bread into the body and blood of Christ, something easily explained in terms of Aristotelian philosophical language. We also know that there were individual enemies of Galileo who, infuriated by the force of his polemics, for he is an engaging and winning polemicist and loves to be on the attack, who inserted into his file before the Inquisition forged papers in which he was instructed prior to the Pope's invitation to discuss the Copernican system, not to discuss it at all. Faced with the instruments of torture, Galileo indeed recanted and spent the remaining years of his life under house imprisonment, forbidden from writing. He wrote, nonetheless, works that were the foundations of modern physics and smuggled them out of his home imprisonment. And for the rest of the 17th century and for the 18th century, he was seen increasingly not merely as a magnificent astronomer and physicist and philosopher and quantifier of our knowledge of the world, but as a symbol of the struggle for an autonomous natural philosophy that could explore God's creation without prior conceptions. Recall, in conclusion, Kepler's sense of discovering what God actually had done and what God had awaited someone to contemplate. For better or worse, in the 20th century, we often think of scientific hypotheses as operational formulae, as tentative, ephemeral understandings of the world. In the work of Kepler and Galileo, there is this sense that finally, with proper method, the human mind for the first time was discovering the real nature of things, and for the first time was looking upon God's work, given proper method, with understanding. It is a dramatic part of the intellectual revolution of the 17th century. Thank you.